Okay, it's time to start. Good morning, everybody. Then we have the big audience online. Good morning. And we will have the seminar today, but I will start from the announcement that just now, half hour ago, Senate of AGH approved the program for space technology. This was a vote, and that was 80 senator, and 80 senator voted for. I think this is good news that we can develop the study, and we will have on board the students. Students from Poland, they are welcome, but also the students from abroad, from University Alliance. I think it will be the new era of the space technology at AGH, University of Krakow. Today we have the seminar, which is very related and very close related to the subject of the space technology, education, campus to cosmos, university researchers experiments in space. That's Dr. BHM Darukesha will give us a view how be a researcher, because he has a long experience in space technology from Indian Space Agency, ISRO, and he will share with us his experience on that. Please, Dr. Darukesha, the floor is yours, please.
Dziękuję. Dzień dobry. What a way to start a seminar with a great announcement. I thank Professor Ul for this opportunity, and I welcome all of you, those in the auditorium and in watching it online. Well, the goal of this presentation is to motivate and facilitate graduate, postgraduate, PhD students and early career professors to conduct their first experiment in space. So these are the disciplines listed that we can target. I intend to offer practical insight into this based on my experience at a space agency, being a co-investigator for several academic research projects, my PhD degree from a university, and being member of a team planning to conduct an experiment on International Space Station. So I believe it also helps the agencies and space industry, essentially because this can lead to meaningful propositions, and their smooth and effective functioning can help all of us. I know this talk is going to be archived at YouTube at CTK AGH. Those of you may watch it later. You may please feel free to pass it on to your friends, leave comments, or ask questions there also. This is how the talk is outlined. Well, first two questions are, why a space experiment? That too, why me? Space is for everyone. Anyone can benefit the space. Also, when the access to space is becoming more easier and easier for everyone, why not a university researcher make the best use of this? Historically, the universities have helped shaping and flourishing the space agencies. For example, Caltech, MIT could help NASA, IISc helped ISRO, University of Tokyo is in ties with JAXA, Stanford University is collaborating with SpaceX. So there is a lot to play. Space experiments can give a career to a university professor, as well as it is high time that universities roll out the startups and companies in space sector. With little change in perspective, several experiments that we conduct on ground can be transformed into an experiment on space. So instead of looking at it as low hanging fruits, possibly we should look at it as that opportunity that offers huge scope for our career. It is heartening to note many universities have taken up a lot of initiatives to explore the initiatives at CTK. I will leave this URL in the YouTube as a comment so that you can browse through that. Funding opportunities are in plenty. Here is a non-exhaustive list of opportunities. Of course, I will leave this link in on YouTube. They include those from space agencies, including the Polish Space Agency, international organizations, private companies, and as an example of research, say journal paper, I've included one. So it is against this POLSA advertisement that call for proposal that CTK is conducting an experiment on board ISS. Most commonly, they appear as announcement of opportunity or call for proposal, but they appear as and when they become available, not on calendar event. So it is good idea to set up alerts and keep visiting these pages. One thing we notice is these proposals are preferred from their jurisdiction like nation or union naturally, but most of them prefer and encourage international collaborations. Some of them are limited to universities, some are for the startups. So if we browse an opportunity, we can always find an eligible university or a startup that we can tie up. And I also encourage all of you to go through these pages because they include the opportunities for summer schools, fellowships that are offered by international organizations, space agencies, and private companies. Well, what would be the evaluation criteria then? Typically, the topics that are clear in objective, promising outcome, feasible to be conducted by the investigator within the time frame, fitting the current priorities of the funding agency and the mission in mind are likely to be considered favorably. Let us not plan something that is ambitious, too complex as our first proposal. We can keep it for the next round of proposals. Additionally, what will help is advanced technology readiness level. Typically 5 and above is better, where we have evaluated our experiment at least in breadboard model in the environment that we intend to say perform the experiment. It also helps when the hardware is small and it is a time bound activity. Within the time frame we should be able to do. They fall into three categories. You are testing something or we are making a measurement. We are demonstrating a technology or we are involving other university students or general public in space experiments. So this is how generally evaluation is considered. As a classic example, I'm just sharing the evaluation criteria for the recent POLSA announcement. This is one of the perfect examples, and here is this page. I'll leave the link on the YouTube so that you can study this in detail and understand how the proposals get evaluated. Further, when there is proposal criteria, when there is evaluation criteria, why not a proposal criteria, at least for us on subjective basis? Our best bet would be proposing those things for which a research project has been completed for a ground application after finding its relevance in space. The reason is this: when we are doing in academic research, what we do, we set up the experiment, we expect some results. Many a time we find new but interesting result. We align ourselves to those new results and write as if we wanted to go there. But see here, nobody has watched us. When we are proposing a space experiment, it gets approved after several review and approval, thinking and assuring the outcome and the experiment the way you are expected to do. We have committed ourselves. So which means we had to do that the way we have committed and within the time frame. What it means is somebody is watching us, and in order, if we do some all that we are, if we propose something that is new in experiment itself, it is a really bad idea. For God's sake, please don't propose anything that is related to a PhD topic. Space science experiment can should not be linked with a PhD topic. PhD thesis can have some portion of the experiment that is conducted on space, but then definitely not a good idea to link it to a PhD topic. Then what for we do? We conduct these experiments to get the university, the researcher to get trained, to expose to the system engineering, and then learn the approaches. Obviously, the publications will roll out. So it is this value addition that the space agencies would look forward, so that in the system, there are more people who can do space experiments. What we are likely to learn in execution is, first thing that we would come across is we would feel there are unreasonable demands from the funding agency or space agency. As we go along, we'll very clearly understand why they are not unreasonable and how important they are. We will be doing lots and lots of documentation. We'll face the reviews, expert reviews in terms of boards and committees. We will learn how do we address the same problem in multiple directions at different stages. Though we will do the document, we will be requiring to redocument, redesign, re-realize, retest, maybe reintegrate, and then fly. So it is this area that designing an experiment, realizing it, testing it, integrating, that's where I have my personal expertise. So this is where the crucial parts of any experiment is going to be. So moving on, then what type of experiments suit better? In order to appreciate that answer, it is better to know what space has got to offer to us and who are all playing in this arena already. If we start climbing at around 10 kilometers, we would see the aeroplanes flying by the side of us. Between 20-25 kilometers, we see the sonde balloons. About 50-70 kilometers, we will see the meteors burning in dazzling light. If we cross 80 or 100 kilometers, there is nothing. So this nothing is space. Space is nothing but nothing. Then what do we study from space? We study the space environment itself at various altitudes, and we study the earth, we study the celestial bodies, interplanetary space, intergalactic space, and the universe. So tangibly, what exactly we do is that we would be planning to send the satellites, the space stations, the human beings to space. In order to achieve that, we need to have rocket technology. We need to have experiments that give that give the benefit of this space technology. And in order to manage all this, we would establish the ground stations. So these are the different aspects wherein as researchers we would be playing. Then what has got space to offer to us? Space is essentially vacuum. So, say at sea level, we would see 760 torrs of pressure. If we go to 10 kilometers, it would come to 170 torr or something. If we go to 400 kilometers, where the human beings are there, I mean, it is earmarked for human activity. Here, there it would be 10 power minus 4 torr. So further deep, if we go to geostationary, now it will go reducing by orders. In fact, deep intergalactic space is supposed to be 10 power minus 20 torr. Then the other, say, other aspect is the radiation. Radiation is second inherent property of the space. We have got bombardment of, say, protons, helium, alpha particles, heavy ions, and beta, the electrons, neutrons, the X-rays, and the gamma rays. These are ionizing type. Among non-ionizing, IR radiations, non-ionizing UV light. So it is continuously being bombarded. The next one is microgravity. Microgravity per se is not an inherent property of space, because we go there, we keep something that keeps revolving. Microgravity situation is created. It's a created property by some object that is moving. It is like free fall. So we would have seen, I'm very sure we all have seen YouTube on, videos where things float. Off gassing or out gassing. This is a unique property of materials. When we keep in space, the vacuum and the temperatures, they exaggerate these property. This is a phenomenon in which if I keep something in space, after some time it disappears. Ultimately, everything turns into hydrogen. But then during this process, it would take days for some materials, months for some materials, and then years for some materials. For example, Teflon. Per day, you would see zero point 0.1 to 0.5%, 0.1 to 0.5 of its mass gets lost. If it is anodized aluminum, it can be negligible. If we put plain aluminum, it would be 0.01 times its mass. Per day, we will be losing. So then the next one is temperature swings. If I'm facing sun, my face will be lit with plus 150 degrees centigrade. My back will experience minus 170 degrees centigrade. So the next thing that is all that space will offer is the isolation when it comes to human beings being present there. It's an unknown area. People are going, staying away, though they are actually 400 kilometers in altitude. We all feel isolated. So this is what space has got to offer. One thing that we need to add to this list is that space is having a real estate. Space, though we say space is unbound and we can go anywhere, that's not going to be the case. Space has got limited space wherein we all will have to work around. Then, who are all playing their role here? We have got space agencies, the private players, startups, the universities, and international bodies trying to regulate these activities. So, what started as a human endeavor out of just curiosity has now become an industry. In order to be playing our meaningful role, our propositions have to be clear, have to be really value added. Then coming to which experiments then suit better. We know what are the unique opportunities as a research lab that space offers. I need to propose those things that can bring out the real change. Vacuum based. So I just listed few topics that can be proposed because there is high vacuum in space. One example, if we take the dielectric discharge, air breakdown. So it is likely to happen at low voltages in space. If I can develop some coating, some material that can withstand much higher voltage levels, we have a point to prove. Similarly, if we go to radiation, this radiation hardened components, definitely they are going to be, we are searching for better and better materials. Seeds undergo mutation in space. What type of mutation can bring us the best yielding and say disease tolerant crops? I'm just taking one example that the focus of today's presentation is to not go into them, but to pick up how do we pick up the ideas, how do we pick up the experiments. Then when it comes to microgravity, things that get affected are combustion, the fluid dynamics, cell growth, things like this. But we should also remember that several chemical reactions that occur at molecular or atomic level, they are not going to be affected by microgravity. So also the experiments related to magnetism, electricity, light, optics, several of them are unaffected. So then when it comes to isolation, psychologists can try out these things, change in cognitive abilities, and they also should not attempt those things that would require large sample sizes and also lifespan. Today, the record number of days a single person has spent in space is for 37 days. So it is just 1.5 year. We cannot expect lifespan studies possible on human beings. So what it says is we can say initiate our space experiment if we are working on these activities, or we can align ourselves to these activities, or we can explore more. So this is where clear objective can easily be identified. This is a first part of the evaluation criteria. Then moving on, mission specific, which means I am calling for proposal for some specific activity and which suits where. For us, we need not look at from that angle, we can look it as a global level. Now, sounding rockets, they fly as high as 80 to 200 kilometers typically. They offer 5 to 10 minutes of, say, space. If I have some experiment ready, I can quickly launch and I can have multiple opportunities. So this is where something that has happened on Sun. So I want to study at the right time, I can fly this. So this is how we should be ready with our experiment, and then we can grab the opportunities to conduct the experiments. This is a orbital module. Typically, the satellite launch vehicles, rockets, after putting their satellite into the intended orbit, they also will continue in that orbit, the last stage at least. That will stay for 2-3 years. Of course, by using the fuel, we can bring it down so that we declutter the space. Typically, even if we do 70, 80 days, we can make it to revolve around the Earth. This is where it performs as orbital module platform where experiments can be done. ISRO has conducted over 30 experiments using this platform. So next opportunities, of course, are satellites in the orbit, the grand ones. They vary in the shape of their orbit, their altitude, and their inclination. If you want to look at sun all the time, you may have to choose sun synchronous orbit. If you want to study the movement of, say, clouds or a, a, to- a storm, it would be better to keep your instrument in the geostationary orbit. So this is how our knowledge will increase. Then they depend on the periodicity, how quickly they can finish one revolution. Typically, the polar satellites complete in 90 minutes. Geostationary satellites, by intention, they take 24 hours. They vary in their weight, power, duration, how long they stay, and the purpose. So it is better that we understand these opportunity when we are proposing our experiment. Then there are deep space missions where we can study not only the Mars, Moon, other planets, but the interplanetary space itself. Our mission planning, our communication links, autonomy, these are best tested on these platforms. Then landers and rovers, these are modern marvels on Moon, Mars, and they offer equally and better opportunities to try out our AI and automation related activities. How best we can combine. Then space stations. Sorry. Space stations. We have got several space stations, and today, till date, the most sophisticated equipment ever spent to space is human being. Human being go there to conduct experiments, and experiments are conducted on human being in space. Then astronauts, they help us conduct our experiments, and the best way to design an experiment that requires some human intelligence would be when we get the opportunities through astronaut. Then of course uncrewed missions. It's not that space agencies are private, or I mean private companies, they simply try sending human being in their first go. They try out their technology. Those platforms offer valuable, say, opportunities. Possibly, if we can universalize, the most challenging topic would be human beings on Moon, and the most would be human beings on Mars. I'm considering typically our lifespan of about next 20, 30 years. So these experiments, an experiment that can be conducted by a human being on Mars is something that would be extremely exciting. So then these choice, is it by choice? We can choose, but if our experiment is ready and fitting multiple platforms, we get better chances. This is where we call mission specific. Then moving on, it would be better to know what is happening in space so that we propose more meaningful, say, propositions. And this would be useful when we say that we want to make potential impact. Though the private players started in 1980s, it's only last 10 years we are seeing the real fruit. And to date, there are 6 companies that take us to the space as a tour, but none of all of them are private players. Then we are seeing the disruptive technologies, not just the reusable launch vehicles, but Wi-Fi from space. Possibly no space agency could ever imagine that it is viable so quickly, so widely. It's now available. So these disruptive ideas are ruling the world, and then when we have something like that, we will be better placed. This is important because space agencies and national, say, government bodies are prioritizing going back to Moon, Mars, asteroids, comets, Venus. All these things are becoming priority. So they offer better funds, frequent funds. If we can develop some experiment that suit these platforms, our chances are much better. Then other thing, as we were mentioning, space is having real limited space, but then there is a congestion. How to declutter this? How to reduce the traffic in space? This is where new ideas are required. Some disruptive ideas are required. So then, as you can see, the LEO, low Earth orbit, is getting filled very fast, and there is an overwhelming number of satellites in LEO. So LEO is a good space to conduct our experiments. And the other factor is climate monitoring from space. This is gaining up momentum. Here is this NASA ISRO synthetic aperture radar, so considered as the costliest ever built remote sensing satellite. This has S-band and L-band synthetic aperture radars being built by ISRO. It's getting uh, launched in February 2025. So this is the trend. And possibly one trend that we might not get an access is making space as a military base. This is inevitable. It happens. It is likely to happen. This is where possibly we may not, we as physical researchers may not be able to make a big role. But then our friends who are working on law, they will be helpful in making the policies, in dealing the ethical implications of going to space and exploiting other planets as a natural resource to us. So these things will this slide will tell us what are the priorities and where the promising potential ideas can be generated. Of course, I'm very sure this is not the exhaustive list. It's only a representative list. We may have to do a bigger, say, search. This is last but two slides. We found an opportunity. We propose. We get approval. What are those things that can make us easy and say effective execution? If we do one execution properly, we will learn a lot and we can establish as a great researcher in this field, and other space agencies, other funding opportunities will flow. So this is where we need to understand few things. Designing has got all freedom of say degrees, all degrees of freedom. You can imagine the way you want the instrument, payload, the sensor. So there is no binding, but always keep in mind that there is something called KISS. Keep it simple, stupid. This is a tag that got coined in 1960s by US Navy to impart the importance of keeping it simple. Simple is beautiful, simple is effective. Minimize the hardware that you need to send to the space. At the earliest, come to a point where you digitize the data, then downlink that data. Don't keep anything that is required that can be done in the ground, need to go to space. Heritage. Or suppose something has been done by any other space agency. Everybody will give highest value to this. So keep looking for those things which have got heritage. Then this is another golden rule. Realize the hardware as early as possible and test it as you are likely to fly. The reason is we might think in our mind, okay, it will work. We will dream. It will say on my computer, it is working. Only when we start realizing, we come to know that there are many constraints under which we may have to work. What are those constraints? Basically, we would come across that some materials are cannot be used, some processes are to be followed because the space equipment was considered to be irreparable. So it is better to build it properly. That is how it started. It's always a good idea to make proto module, flight module. Then one thing that we normally tend to forget is we want our equipment instrument to work in space. Fine. We should also remember that it has to work in our lab. It has to work on the launch pad. It has to survive the launch vibration, shock, and transfer orbit shocks. Even in space, it has to work in eclipse. If we look at our design, considering all this input, our designs will improve. We can offer better, say, instrument. Other aspect that we normally tend to miss is the interfaces. I build the instrument and we expect the space agency to give me what I want. the way I want to place. Generally, that's not going to be the case. Space agencies, funding agencies consider university researchers as we are helping them. So, means university researchers' responsibility is to know how is this mechanical thermal interface, how I can give electrical connection, to what extent. Based on that, it is better to design. Then we normally build it for performance, as if we will be ready to address any issue as we do in the lab. But we should better build it for repeatability, reworkability, modularity. When we are building for these attributes, our designs will improve. We need to ensure the reliability. There are several practices followed in space industry and in aviation industry. Derating means a component can be used at its 50-60% of the rated value. Accelerated life test to bring out the failure modes, failure mechanisms, build in the redundancies. And we would need thermo vacuum chambers, vibration shakers, sun simulators, radiation chambers to test our equipment. It would be better idea to identify the facilities, talk to them, then build. Also, the standards of testing. We, as investigator of a scientific instrument, I can dictate what the way my instrument can be tested. But the same thing is not true when space agencies require us to prove that my instrument will not harm other instruments, which means there are established test procedures. Tests have to be conducted in that manner only. So it's always better to, anyway, we are going to face this problem. Let us know what are the challenges, then start building. Then the last slide, project management. Typically, there are two schools of thought, having parallel level of expertise from different disciplines, or having one or two people working for project management, getting the best out of people from the different discipline. So we will leave it to you, like the best you want, you can choose. Personally, I would feel the second one would be better. Do you need an industry partner? Yes, definitely strongly recommended, because in your experiment, only variable should be you. Rest all should have been proven so that we are better placed in better hands. One golden rule in writing the document is one information in one place. Suppose lab temperature you need to mention in three different documents. Whichever is the first document that you generate, write there that my lab temperature is this. In the second document, lab temperature, refer to the document one. This avoids lot of inconsistencies. This is a golden rule. Then we would be facing expert reviews from different people. Remember, in space agencies, they have built their expertise over decades, and they know what they are doing and they are what they are good at. But as a researcher, you would be facing all of them. There is a safety review separately, integration team, science team, operations team. They work in isolation as we look at, but they all will be working as a team inside the space agency. But we will be facing them individually. We are facing most experienced people in their domain. So we will be learning lot many these things. One thing that we will learn is critical thinking. No matter what happens to our experiment, definitely we will learn by interacting. We will learn what critical thinking is. We will know how the different management systems are being practiced. That will definitely help us, not only professionally, even personally, it will help. So, at least for these reasons, I strongly encourage every student to think, propose, and conduct experiments. So, what I would say is use this presentation or slide as a checklist when you come across a proposal, when you are proposing proposal is being discussed at the time of design, testing, execution. So this can be used as a basic checklist and you can build it on. So I strongly wish and hope that most of you would come up with your first experiment in space, and those watching online also, uh, they will also make use of these opportunities. And I wish you all the very best. Let your experiment take off very soon. Thank you so much. If there are questions, I'll be happy to answer. Online, Magda may please help me.
Oh, I have.
Yeah.
Well, yeah.
Yeah.
So, would you mind telling us something more about your hands-on experience with Indian Space Research Organization? So I noted the logo in the top right corner, so that's why I asked.
Sure. I did my MSc Physics and directly got a job in Indian Space Research Organization. I worked in a center where that builds all the Indian satellites are built, the ISRO Satellite Center during that time. So when you are joining a space agency, you'll be put into some group, some division. Similarly, I was put into one division like hybrid microcircuits. These microwave modules, the communication between the spacecraft and the ground station happens in microwave. So these microwave modules, like when I send the signal, the antenna will receive, it goes to the low noise amplifier, mixer, and the digital circuit. Then when the satellite wants to send us the information, it would be digital to analog conversion, amplification, and then pushing. So these modules, when I joined in 98, they were imported. My supervisor, me, and my colleague, subordinate, with 5 years of say effort, we made them indigenously. Since then, GSAT 3 was launched in 2003. Since then, all the Indian modules, all these modules, all on all Indian satellites have been built in our lab. So my expertise comes in, say, over beyond that, I could help people build their instruments, sensors, payloads. So my expertise in say PhD is interaction of ionizing radiations with nanomaterials. So these are my expertise. Of course, when we had to design, realize, test, we also should know where the final usage is, and we also should know who are all going to review. So thank you.
Now we will continue this experiment with nanomaterials for space. We have the experiment on International Space Stations related to the nanomaterials, but also we will expand this research with Solaris accelerator here in Krakow, and we will test nanomaterials within different kind of radiation, because they can generate any radiation if we need.
Yes.
That's to the students are welcome to our experiment and to our research in this field. This is very important for sensor design, for medicine, space medicine, and sensors dedicated for space. That's it's our goal to develop these materials. Have you more questions?
There is one question that economic scale. What is the biggest hurdle you experienced in working with large international agencies?
Biggest hurdle possibly would be to understand the requirement of documentation and sticking to that. Normally, as academicians, we tend to conduct the experiment and then build the document. When it comes to space experiments, definitely documentation is first. We might change the documentation. That's why you will see document revision 1, version 2, version 3, all this. But visualizing that, I might my journey would encounter this, and then go finding a solution for that is a great hurdle, and that's where everyone will enjoy. So non-technical hurdle is this. Of course, technical hurdles, there will be plenty. and they make our life interesting. So we should embrace them as if they are the opportunities to overcome.
Dreaming to be on the moon, to be on the Mars, and have such an experience. That is a great experience. But the question is, what is the advantage for the Earth and the people on the Earth due to some of us are going to the moon and to the Mars and walk to the Mars and make some experiment on the Mars? What is the advantage? Because I understand that if we are doing some investment in the new space is dedicated for the Earth and humanities, yeah, then I know direct. We have GPS, we have communication, we have Earth observation, we can predict the meteorological disaster and so on and so on. Yeah, but what is the advantage of this mission to Luna and Mars with the people?
Yeah, that's a wonderful question, Professor. Thank you so much. Really, it has, say, tangible benefits and non-tangible benefits, the space research. So tangible benefits, of course, we found something that exists only in the, say, in space, or we do some manufacturing. Helium was detected in the solar corona first, then it was detected in on the ground.
But it can be.
Yes.
We can send robots, harvester, conveyors, any other kind of appliances, and to make the exploitation of such minerals. That is, I can say, possible and planned. Yeah?
Yes.
But what is the reason that we send people there?
Yes, when we go to the moon, when we look at the Earth, we look at Earth as a different, with a different perspective. We have no boundaries. The way our map shows with different colors, the boundaries, continents, Earth is not supposed to be looked at the way we see on our map. So as a whole, we are representing the human being. In fact, the search for extraterrestrial intelligence, the search for aliens, has a notion that if we find aliens somewhere, at least on that day, everyone, all 820 crore people on the earth will unite, because we'll have somebody to compete with in common. So maybe these are non-tangible, but they have a lot of value with space research, Professor.
From the research point of view, it's excellent, yeah. But from the point of view of the advantages for Earth, I am discussing always what is better, to send robots or to send that it's more intelligent in the appliances. It's artificial intelligence, but they can make some more complex tasks against people on the moon, on the Mars, and what is the reason? But of course, this is open questions, and everybody is discussing on them. This is a hot topic now. It's human missions that we are also doing some research on that. We are organizing habitats at the level up, and because the people wants to go there, yeah,
Yes.
wants to go to the space. If you want to go as a tourist, you should be also trained. Yeah, this is not like that I go how I go to the tram and we are driving. This is impossible to go to the rocket and to be moved to the space and see and back. This is impossible. It should previously pre-tour trainings, pre-tour education,
Yes.
and so on. That is important. Yeah, and we will have here the possibility to train future space tourists. In fact, yeah,
That would be nice.
yeah, yeah.
So coming from academia, one of the problems that I face executing any space project is the notion of how standards are applied. One of the issues that we have in academia is we don't have a lot of standard procedures followed for a lot of activities in the lab. And this starts off with the application of military standards for some of the hardware, down to, I would say, automotive grade standards, which are also available. So for the researchers to start this journey, what is his understanding of the standards that he needs to have to actually start this journey? So that's more of a general question, but very applicable for it.
Yes, that's a, I mean, it's an intriguing one. So it's a very interesting question. Essentially, these standards, aerospace, the aviation industry demanded huge amount of reliability. Reliability is an engineering concept. I can never say that my system will work under all circumstances for all the time to come. But we had to quantify this. Suppose, for example, testing is done at from minus 55 degrees centigrade to plus 50 degrees centigrade. Why only these numbers? Because when these tests were performed, industry could offer the systems that can swing between these numbers very quickly. If I mathematically calculate, I reach to a point of 99.99%, maybe 6 sigma, 10 power, one failure allowed in 10 power 6, 6 sigma reliability. So when this is pushed, people believed, okay, there is no further point in pushing it further, but let us find out where the weakest link is. That is where we do the failure analysis mode, the analysis. So these standards evolved because we want the best, but there is engineering limitation for this. There is budget limitation for this. There is time limitation for this. Today, let us do this much to ensure the reliability to this extent. Tomorrow, these standards might change, but more or less, they have been there. The standards have been there for last 3, 4, 5 decades, and we are following, and they are continuously getting improved. So from a research point of view, researchers point of view, we had to appreciate that someone designed this, someone tested this, someone will assure this reliability, and I should go for this. So this is beyond the science that we learn. Our experiment will give us some results, but learning this, that this is what best can be done. There are several experiments that can be proposed to improvise these standards. So essentially, these standards are an engineering collective effort to see how best I can test, how I can quantify my reliability based on what is available, what can be done. So that's an idea.
Okay, thank you very much. Okay.
Sustainability issues in your design work and how were these challenges addressed?
Okay, that's a very good one, because sustainability is something that all of us are caring. Sustainability can take the shape of decluttering the space, and say, for example, India and France made this megatropics satellite. This outlived its life. It was intended for some 5, 6 years. It lived for 8, 9 years also. Still, the propellant was available. Now, if we leave it, it occupies one slot in the space. But then last year, it was made a controlled re-entry into the, say, Nemo point, that is into the Pacific Ocean, by burning its fuel. So this is a sustainability thing. But now the challenge would be, what do we do with those things that are not having any fuel, that cannot be communicated to, that don't have any signal? That's like a dead body, they are revolving. So this is from the agency perspective. Sustainability wise, yes, restriction hazardous substances, ROHS, is a big initiative, but unfortunately we have not been able to find out a best substitute for, say, tin lead solder. 6337 composition. The way it works is beautiful. It's an eutectic solder, very low say, eutectic temperature of 183 degrees centigrade. Whenever we use SN63, we know that we are using something not that good, but there is no replacement. SN62 is tried. It has its limitations. Pure tin has whisker growth. So this is a great challenge, that one of the challenges with respect to sustainability. We'll be very happy if someone can come up with either a solder or any other material, even a polymer or some other method of replacing say SN63 solder. This is a, to me, I would consider this as a great challenge. Possibly the next one that I can quote is gallium arsenide. Both are bad for say environment, but all microwave modules depend mostly on gallium arsenide as a substrate because of the higher electron mobility that it offers, higher radiation levels it can tolerate. But then we should be finding out quick replacement for these things. There are plenty that we can work on to make, say, I mean, space science and technology more sustainable.
Okay. Can leave the room, but I have the last question.
Yes, Professor.
That you show the way from the campus to the space. But we know that many of technologies which we discovered for the space, we are using on the Earth. It means that it's a way from campus, from space to campus. This is an opposite way. How it works, and this exists or not?
Yes, definitely it is existing. The way, I mean, Velcro that we are working with is, it was meant to be used in space. Now we know how best we are using the pencils, graphite pencils, and in fact, the internet itself was considered. It is a DARPA project that led to this.
Computer mouse is the best example.
Yes.
It was designed for space applications, but now everybody is using that.
Yes, I think that would be a good idea to have a compilation of spin-offs from space technology, and we can work on what else can be bought from there. Maybe CTK we can plan.
But in fact, we should, if we are planning the experiment, we should think about coming back to the Earth. Yeah.
Right.
In my opinion, this is very important. If we planning the experiment to go up, that we should also plan the reverse way
Yes.
to be on the Earth with the solution. Yeah. In my opinion, this is crucial for the success, business success. That is in space we will not do the business. Business is here. Business is related to the Earth, not to the space. Yeah.
So,
okay. Thank you. Have you, Krzysztof?
I just have a last remark more for the younger. Instance is smart to the campus, to the cosmos, okay, now.
Yeah, it works.
That's right. Okay, now it works. I encourage you to use the opportunity just to talk to Dr. Darukesha. He will be in here at least till mid of the next year. He has a lot of the experience, and I think for you, this will be the first step from the campus to Cosmos, talking to Dr. Darukesha. He will be also leading one of the courses for the new space program for the master's level, which would start next March, if you're looking for this opportunity as well. And I think there is also some course that Dr. Darukesha has something on the presentation right now.
Yes, I mean, I thought this presentation today's was focusing on about the journey. It was touching upon the representative examples.
If you show this is a one-way journey, but we need to return.
Yes.
Sure.
Yes. So these are the topics that we can delve into in more, I mean, in depth technically. So I look forward to have many of you, those who are watching online or who are likely to watch in future also. They also can propose, maybe when we have good number of students, we can conduct this short course and go into the technical aspects in depth. I look forward for that. Thank you for this opportunity.
Yeah, thank you very much. Thank you, all participants. Thank you, online participants too. How many people we had? 20 online. It's good. Okay.
Yes.
Thank you once again.
Thank you, Professor.